This unit is split into two main sections. The first looks at metals, the second looks at acids and alkalis. Let's look at the first section, starting with the differences between metals and non-metals. All elements can be divided up into two groups, metals and non-metals, and each of these groups have similar properties. This group is metals. We can see they are all shiny solids at room temperature, except mercury, which is a liquid. They're good conductors of heat and electricity when solid or liquid, and some, like iron, are magnetic. Non-metals, on the other hand, are a very diverse group of elements. Half of them are gases at room temperature. For example, here are chlorine and oxygen, gases. Other non-metals are carbon and sulfur, which are solids, and bromine, which is a liquid at room temperature. Their appearance is dull, they're poor conductors of electricity, and they are never magnetic. For your test, you need to know the differences between metals and non-metals. Metals are usually strong and flexible, whereas non-metals are generally weak and break easily. Metals, apart from mercury, have high melting points. Non-metals have low melting points. Metals are usually silver-coloured, whereas non-metals are different colours. Metals are good conductors of electricity, non-metals poor. Some metals are magnetic, non-metals aren't. But be warned, don't just rely on physical properties alone to sort out metals from non-metals. Graphite is a form of carbon, another non-metal, but it is a good conductor of electricity. And mercury, although it is a metal, is always a liquid at room temperature. We'll be examining the properties of metals in more detail in the next section. This section takes a closer look at the physical properties of metals. Their chemical properties are covered in the next section. Metals may look and feel very similar, but to find out what metal is good for what job, we need to take a closer look at their physical properties.
People have understood some of the properties of materials for a long time. The Egyptians, for instance, knew that gold doesn't react with air and corrode like some other metals.
It's a property called being inert. Inert means that gold doesn't react easily with other materials, and that includes the chemicals in our bodies. So they used it for filling and replacing teeth.
And 3,000 years later, dentists are still making use of this property. In fact, almost 60 tonnes of gold a year goes into our mouths.
It's the combination of properties in metals that makes them useful for different purposes. This cutlery has been coated with silver, so it not only looks good, but it's safe to put in your mouth. Flexibility is also an important property, as metals can be flattened and moulded, yet still keep their strength. For instance, aluminium is often used for cans. But there are some other important properties that you can't see. And the most important one is conductivity, the ability to carry an electric current. And copper is a brilliant conductor of electricity. But it's not just copper that has hidden properties.
But for the users and designers, it's more than just one property of material that's of interest. It's a whole range of properties. So for gold, well, gold is ductile, so it's easy to work with. It doesn't corrode, so it lasts a long time. We can work with it at minuscule levels. And it's a good conductor of electricity. It's this combination of properties that means we use gold in almost every electrical appliance.
Gold is at the very heart of the electronic age.
So we've looked at the physical properties of metals. We're now going to move on to look at the chemical properties of metals. We can also study metals by looking at their chemical properties. Some metals willingly combine with other elements to form new compounds, while others will not react at all. This is because some metals are more reactive than others, and we can place them in order of how vigorously they react. This order is called the reactivity series. We're now going to look at several different metals and see what happens first when we burn them in air, then when we put them in water, and then finally in dilute acid. Let's start with burning in air and see what happens to the metals magnesium, iron and copper. First of all, magnesium. As we can see, magnesium burns very brightly in air. It readily combines with oxygen to form the compound magnesium oxide. The iron in the form of iron wool burns less brightly. And with the metal copper, there is no reaction at all. We can write word equations for them. Magnesium and oxygen makes magnesium oxide. And iron and oxygen makes iron oxide. So, with burning, magnesium is the most reactive. Then comes iron, and finally, the least reactive metal is copper. Metals at the top of the list are the most reactive, and the metals at the bottom of the list are the least reactive. Let's look at another set of reactions. This time, the metal elements potassium, magnesium, and lead, and see how they react with water. The metal potassium is so reactive it has to be kept under oil and handled very carefully. The reaction with water is very vigorous, producing hydrogen gas and a lot of heat and light. Let's now try magnesium. The reaction is far less dramatic. The tiny bubbles along the metal strip are bubbles of hydrogen gas, so this metal is also reacting with water. And finally, lead, where there is no reaction with cold water at all. The general word equation for a metal reacting with water is the metal plus water equals metal hydroxide plus hydrogen. So for potassium reacting with water, the equation looks like this. Potassium plus water equals potassium hydroxide plus hydrogen. Why not stop the tape and try and write out the word equation for magnesium, as this is very good practice for test questions. So if we go back to our reactivity series, we can put potassium near the top, above magnesium, and lead appears near the bottom. Now the metals always have the same place in this order, so this means we can make predictions about how different metals are going to react. So what will happen if we add them to dilute acid? Well, we can't use potassium or sodium at the top of the table, as the reactions would be explosive. So let's try magnesium, which is below potassium, then zinc, and then copper. And according to this list, copper should have the slowest reaction. Dilute hydrochloric acid is added to the metal magnesium, and straight away the reaction fizzes, letting off bubbles of hydrogen gas which can be tested using a lighted splint.
Ready? Now let's try zinc. Okay.
Powdered zinc is used, and again with dilute hydrochloric acid, the reaction is far less vigorous, but hydrogen gas can still be tested for.
Let's do the copper now.
Shavings of copper are used, and this time, when the acid is added, there is no reaction. So the order going from the most reactive is magnesium, then zinc, and finally copper. And we can also write word equations for these reactions. When metals react with acids, the pattern follows. Metal plus acid makes metal salt plus hydrogen. So, for example, with magnesium, the word equation is magnesium plus hydrochloric acid makes magnesium chloride, the metal salt, plus hydrogen. So the key points are that different metals react with oxygen in the air, water, and dilute acids at different rates. And that the reactivity series is a list of metals in order of reactivity. Metals at the top of the list are the most reactive, and metals at the bottom least reactive. Coke, vinegar, apples and lemons. All these substances taste sharp. This lemon contains an acid, and acids always have a sour taste. Now the opposite of acid is alkali. Soaps, oven cleaner and washing powder contain alkalis. But how do you tell which is which without poisoning yourself?
So why does it matter if a soap or toothpaste is an acid or alkali?
Well, your body is made up of a lot of different chemicals. Some of them are acidic, some of them are alkaline, some are neutral. And so it's important that the products don't react in the wrong way with the chemicals in your body.
Right, but how can you tell then if something is either an acid or alkali? Do you just guess?
Well, no, we don't actually. We've got something called universal indicator paper, and it comes in these little packs here. And this changes colour depending on how acid or how alkaline, whatever it is. We've got some ordinary cola here, and if I dip this in, what you can see there?
Ah, now that's gone quite pinkish, sort of orangey colour.
Here I've got a table that shows the range that you can go through, and it goes through from red, which is acid, through to blue.
So that must be an acid?
That is right, that's an acid. So an acid will turn towards the orange or the red colour. And here I've got some ordinary household bleach. And then if we test this again, what do you see there?
Wow, now that's very blue, greenish. So that's an alkali.
Alkali.
Right.
Liquids and solutions that are neither acidic nor alkaline are called neutral. Water is a good example of a neutral liquid. So for your test, you should know that acids are compounds that contain the element hydrogen, and a base is a metal oxide. When a base dissolves in water, it forms an alkali. Acids take part in some important chemical reactions. We saw earlier in this unit the reactions of acids and metals. These reactions are all very similar and can be summarised in the word equation. Metal plus acid makes metal salt plus hydrogen. You also need to be familiar with how acids react with bases and with metal carbonates. Dilute sulfuric acid is added to the metal base copper oxide, which produces water and the dissolved salt. Once filtered, the water in the blue solution can be evaporated away to leave blue crystals of the salt copper sulfate. Here, sulfuric acid with copper oxide makes the salt copper sulfate plus water.
What are you putting in?
Sodium carbonate.
The third pattern you need to learn about acids is their reactions with carbonates. This time, hydrochloric acid is mixed with sodium carbonate.
How much?
The fizzing is due to the gas carbon dioxide being released, so the word equation is acid plus metal carbonate makes a metal salt plus water plus carbon dioxide. So with this reaction, we have hydrochloric acid plus sodium carbonate makes sodium chloride plus water plus carbon dioxide. Reactions of acids with alkalis are called neutralization reactions. Neutralization occurs when the right amounts of acid and alkali react to cancel each other out, forming a salt and water which is neutral.
Now, if an acid reacts with an alkali, a number of things can happen depending on the two you're mixing together.
And one useful one is when you mix the right amount of acid, this one has a pH of 4, with the right amount of alkali, this has a pH of 11. The acid and the alkali neutralise each other.
Neutralise? Ah, that must be what happens to the sting.
So, if a wasp sting needs vinegar, which is slightly acidic, to neutralise it,
It must mean that the sting itself is slightly alkaline.
So a bee sting must be acidic because it needs the alkaline bicarbonate of soda to neutralise it.
Look, it says here that bicarbonate of soda is also taken for indigestion.
That's because it's bubbly and helps break down the food in the stomach.
or somehow it makes all the windy gas come out.
Maybe it helps because there's some kind of chemical reaction. And that means we've got acid in our stomach.
No, we don't.
Stella, what is in our stomach?
I can show you. This is a model of the stomach. And inside, there are lots of different chemicals, including, would you believe it, hydrochloric acid, which is a very strong acid with a pH of 2.
And that acid is there to aid digestion.
Now, if the acid builds up, you can start to feel unwell, a bit windy, you know the feeling. So, to calm the stomach, you have to neutralise the acid by adding an alkaline substance. Now, these indigestion tablets contain bicarbonate of soda, which is the same sort of alkaline you can use on bee stings. So, when the acid and alkaline react, you get a salt plus water. Now, the salt is harmless and the water is neutral, so it calms your stomach.
So the word equation you need to know for neutralization reactions is acid plus alkali makes a salt plus water. And with universal indicator, when the right amounts of acid and alkali are added, the solution will turn green, neutral. So you should memorize the pattern of the reactions of acids. Acid plus a metal base always makes a salt plus water. And an acid and a metal carbonate always makes a salt plus water plus carbon dioxide. And the reactions between acids and alkalis are called neutralization reactions, and these reactions can be summed up in a word equation. Acid plus alkali makes salt plus water. That brings us to the end of the chemistry units in this programme. Remember, there are more in the first science programme in the Bite-Size series. Don't forget the book and our unique website, which will help you with more info and practice questions. Now we're going to move on to the physics units, or if you want, why not take a break? Remember, it's your choice.
Unfortunately, through the last week I crammed in all the facts possible, but I wouldn't recommend this as a way to go. Putting too many facts in your brain at one time can force out other facts which you wanted to remember.
When I revise, I make flashcards because it has an answer on one side and a question on the other, and it's easy to test yourself.
When you revise, don't just reread your notes. We know that you have to process them in some way. Draw them, diagrams, colour, spider charts, anything that will help you to remember.